Well, Konrad, next speaker. Konrad, can you hear me? Hi there, Konrad. Konrad.
Yes, hello.
Как дела? Как твое настроение?
How are you doing? How are you feeling?
Awesome. I'm really not happy not being in Novosibirsk, but we have to thank you, COVID, for that, probably.
Ну, скоро, я думаю, все равно это закончится и будет...
Well, soon it will all be over and you'll come to Novosibirsk, definitely.
Okay.
Сегодня ты будешь...
I hope so. I
Today-
hope so. Really.
собственного рантайма.
You'll be talking about how you made your own runtime. And I'm really curious, how did you get to that? I mean, why? What made you do this? Maybe you are not happy about the current runtime somehow.
No, absolutely not because of that. I really love the current runtime. In fact, I'm answering this question during the talk, but just as a kind of short answer, it is because of fun and learning. So I simply, one day, I don't remember at which and where I was, I thought, okay, but what if we could write .NET runtime as a running on .NET runtime? Let's check it. And it is just step-by-step decision to follow this. And we will see when it will end. You know,
What do you think,
one
Konrad?
thing,
Yeah?
Keep going.
Please continue.
one funny thing about this project is it is so totally unuseful that it is just fun to write it. Like, I don't expect anyone will use it because it will take too much time to do something super useful. So it is nice. I like, just plain fun.
Интересно, я вот размышлял...
Interesting. I've been thinking about why you would need your own runtime, and on a general principle, if there's some very specific hardware and you really want to launch .NET on it, then your own runtime will save the day.
Yes, that's true. That's true. I mean, does like .NET itself, .NET Core is doing a lot of work to cover most typical platforms, but just having more runtimes is better. Like, we have .NET runtime, which is managed time. So if we are able to run it on different platforms, we will see what it will bring. Like, learning, fun, and experiments and research are the main benefits of doing something which is not the super production ready main runtime. And then we can port back some knowledge to the main runtime. For example, it is happening in Java. Like, they have a lot of experiment runtimes, and learning and a lot of research is being done, and then they are just moving this knowledge to the main runtime.
Ну что же, я уже сам...
Well, I am all impatient about your presentation, so the floor goes to you. Please continue.
Awesome. Thank you. So hello again. Hello everyone. Not again. As I said in the introduction, I'm super not happy that I cannot be done in place, but this is how the things are working now. So my talk today is pretty nerdy one, which is about Mobius, writing your own .NET runtime, which is running on .NET runtime. So let's move. My name is Konrad Kokosa. As I said, I'm on Twitter. As far as I know, Twitter is not so super popular in Russia, but if you have a Twitter, you can follow me there. I'm a guy related to performance, .NET stuff, low-level stuff, and all the things. So writing own runtime is just one of the things that I'm doing on this field. And the very first question is, have you ever wondered how .NET runtime works? But you were probably didn't have any good motivation to go deep inside. And Mobius and this talk and whole the idea is something around the motivation to go deep into the .NET runtimes internals. Then another question for you is even maybe have you ever dreamed of contributing to .NET runtime? And probably even if you did, you were afraid of doing that because it is so super huge amount of code, so tremendously popular, so tremendously important that it is, and the learning curve to add anything to .NET runtime, I mean the .NET Core, which is open sourced, is super scary. Because of that, no one is doing anything to .NET Core. Maybe besides Ben Adams, which is doing a lot of awesome things, not working for Microsoft. But in general, we are afraid because it is huge code base, and having smaller runtime, which is just on opposite side, which is just motivating people to experiment, to contribute, is something that may be beneficial for .NET ecosystem. But the very first question for everyone watching me now, or just that will be watching the recording, is why you have ever think about writing such an exotic thing like a runtime running on the runtime. So the very first the question that we should answer is what is .NET by itself? And we all know what .NET is for sure because we are using .NET, but from the formal perspective, .NET is just an open specification, a technical standard, which is somehow standardized about description of what the executable code is, what the runtime should do to execute it, and some high-level languages, how they should be constructed to be also aligned with this standard. So .NET is an open specification. It has been specified in Common Language Infrastructure Standard, which is called ECMA 335. And I noticed recently I have here a misspelling. The name of it is Common Language Infrastructure. So it is ECMA 335 Common Language Infrastructure, which is the Bible, let's say, of the .NET. It is just description of it, what the .NET is and what should be done to have something .NET compliant, let's say. And by itself, it is interesting read. So if you are interested in low-level stuff, you can read it. It is open. It is free. You can download the PDF. If you are scared of the size of it, you can start from the blog post from Matt Walren, which is just kind of high-level overview what's inside. So .NET is a standard. It is open sourced, let's say, standard in the meaning everyone can read it and everyone can implement it. It consists of a few pieces. This common language infrastructure, which is the core name of the .NET, is consisting of 4 parts. It consists of the common type system, which is description of what data types we should use in .NET. There is a metadata part, which is description of how the information about the program itself is stored, and it is also well standardized. Then we have Common Language Specification, CLS, a special set of rules for languages that would like to interoperate with each other, and I will return to this CLS compliance in a moment. And then the most interesting for us is the virtual execution system, which is the part describing how we should load and execute programs that are written in this CLI compatible way. This is just a different fancy name for the runtime itself. Obviously, this runtime should be aware of the common type system, of the metadata, to make this execution possible. And all this is, in the end, using CLI, CAL, Common Intermediate Language, which is a common description of your program, also aligned with ECMA 335, which is super detailed described there. So we have all these pieces. All those pieces are open. You can read it and you can start implementing your own .NET because it's all open. And one side note about common type system versus common language specification. So common language specification is a subset of a common type system because .NET we can have multiple languages interop with each other. So we can write in Visual, Visual Basic, in C#, in F#, maybe in different languages, and every language can use common type system. But there is a subset called common language specification, which is set of the common type system that every language should only use if we would like to interop with the other languages. And what is funny and interesting, C# is not CLS compliant by default. If we would like to make our program written in C# CLS compliant, we should enable it with the help of this CLS compliant attribute. And by setting it to true, we'll see that out of a sudden, a lot of parts of our application is not CLS compliant. CLS compliant, for example, we cannot have public fields which are starting with underscore because it is not aligned with the CLS standard, because maybe there are some different languages that doesn't allow us to have public fields which are starting with underscore. But we don't care because 99% of our code is written in C# and 99% of libraries are written in C#. So most typically we don't care about it. And I'm mentioning it as a funny fact and also as a side note for the runtime creator that we should not care about it. It is something about the compilers, about the languages. So now let's move to the virtual execution system, which is a fancy name for just the runtime. And what it is just a piece of code. It is just a program. No magic here. It is not a virtual machine virtualizing something on the computer using CPUs in a magic ways. It is just a program that is this responsibility to take a CLIL code and execute it. That's all. Knowing the common type system, knowing the metadata, how to interpret, because the input for the runtime typically is a file, an assembly that contains a program that we have compiled. And we may ignore common language specification. And so currently we have some implementations of ECMA 335. Obviously, there is a .NET Framework, there is .NET Core, and Mono, and they are the three mainstream implementations. Mono is getting popular because it runs Blazor, it runs Xamarin, it runs part of Unity. There were some less popular, like for example, rest in peace .NET Compact Framework, which is was designed for small devices. Even smaller .NET Micro Framework, which is even open sourced for even smaller devices, microcontrollers. We can treat this as a kind of exotic implementations that are not longer living a lot. At least I don't know anyone using it currently. There were some experimental, academical, open source implementations like Rotor, which was also called Shared Source Common Language Infrastructure. It was at some day Microsoft has created its own .NET runtime implementation that was designed to be open sourced before .NET Core to show how you can implement .NET runtime, and the sole purpose of it was learning and experimenting and research for academical purposes. You have here open source runtime and experiment with it. But this was not such a huge success. In the end, no one used. I was not seeing a lot of research around this. There was also a .NET Anywhere, which is open source runtime written by a single man, Chris Bacon from Google, and that is pretty awesome. There are talks about it. You can find it on YouTube. It is open sourced on GitHub. .NET Anywhere, written in C. and it was used as initial prototype of Blazor, which is an interesting historical fact. And a very exotic .gnu portable.net, which are just closed and no longer existing. So in the end, we don't have so many implementations of .NET runtimes. But what is common here that all happens to be written in C and C++. Obviously, it is an obvious choice when writing something that should be fast, and it is pretty low level. We are writing it in a low-level languages like C or C++. Currently, probably it is a matter of time of .NET runtime written in Rust, which is a new shiny language for low-level stuff. But it's all unmanaged. The question is then, what part of the runtime should be written in this unmanaged C++, let's say, code? And it is not so obvious like everything. This seems to be obvious that everything should be written in C++, for example, but it is not so obvious. And the decision is what part of it we would like to have it in C++. We see this in .NET Core, for example, which is obviously written in C++, but more and more parts of it are being ported to C#. One of the reasons is because of the better maintainability. It is always nicer to write something in C#, which is more safe language. It is faster to write there fast, good code. So it is just nice for .NET ecosystem and .NET related people to write parts of the runtime in C#. And there is also another pretty important benefit. If some part of the runtime has been ported from unmanaged part to the managed part, there are less transitions between the runtime and the application and the part of the library itself. And those transitions are the overhead, so we can really benefit of getting rid of the unmanaged part and moving them to C#. And this is happening. So, for example, sorting primitives has been already ported to C#. When before 3.1, as far as I remember, or 3.0 .NET Core, when you were sorting something, you were using, in the end, unmanaged code from the runtime itself, but those primitives were ported to C#. So now the C# code is responsible for sorting, and this allows to get rid of this managed and managed transition, which also introduces much better GC pauses, because GC is now able to interoperate with this code better. And this is an example. There is also ongoing work, for example, to port all the threadpool code from unmanaged runtime part to the managed part. And also some even experiments to move at least some parts of the JIT or the GC to C#. So this is an ongoing work which makes sense. Also, there is this CoreRT runtime, maybe you are aware of it. Its goal was to write as much of the runtime in C# as possible, like the whole type system was ported to C# and many other parts. Still, some crucial parts like GC or JIT were mostly written in C++ still. And this is a little bit postponed project, but it is for sure existing open source. You can also look around. So there is this little or bigger movement of porting some C++ code of the runtime to C#. But the question is, okay, so let's move further. What if the whole managed runtime is written in the managed environment in the C# and there is literally no native or C++ code? Has anyone tried to do that? And this is the question that has come to my mind a few months ago or 1 year ago, I don't remember, whether it is completely stupid idea or maybe not. And then I started research, and obviously in JVM world, a lot of things are happening because they had huge community, which also has this open source and academic approach pretty popular. So they have some projects like that. For example, they have a Graal VM, which is pretty similar to what we have as a core RT. So it is a virtual machine, JVM virtual machine, where JIT and most parts of it was written in Java itself. but it is similar to CoreRT. But they have also more experimental research-based virtual machine, which is called yikes RVM. I'm not sure how I should spell it, so I will call it yikes RVM. It is a JVM virtual machine written in Java. It requires only very small part of C-sharp, of C-based bootstrapping, but the whole runtime is written in Java. It is self-hosted, so Java code runs on itself without requiring a second virtual machine. Something a little bit mind-blowing. So this yikes RVM seems to be pretty similar things to what I thought will be a new idea, and I called Mobius. So what this yikes RVM is saying about itself on their own pages, they are describing this virtual machine as a super flexible open testbed to prototype virtual machine technologies and for experiments, because obviously it is much easier to experiment in Java than in C++, for example. So as they are saying, it is a super useful vehicle for research, and it triggered over almost 200 publications, for example, about virtual machine technologies in JVM context, because it has much better learning curve. It is much easier to start to experiment in this environment than in a full production-ready JVM virtual machine. So I thought, okay, so it seems to be a really nice idea, and probably maybe I can do it. Based on that, they were doing that, and it is popular, and it has some usages. So in the end, why it is, for me personally, it makes a little bit sense to do something such exotic thing. For research and experiments, as I mentioned many times, it is as much easier and faster to prototype some parts of the runtime, especially various JIT technologies or GC implementations or the runtime itself. Everything is C#, so it is much better to use all the .NET Visual Studio debugging ecosystem and so on. Also, it is learning because obviously, when we do runtime, we learn about how the runtime works and how this internal dependencies may be handled and so on and so on. So learning is awesome here. And it is also really inviting because you, as I said, and I was also scared to look at the C++ code of the .NET Core, but when you have a solution which is just a C# code that is compiling and you have a runtime, it is much easier to start to do something there. Also, it is a super nice way of abusing, or another word, learning C# when there are all those low-level stuff being added to C# like span, stackalog, unsafe class. We have function pointers or other things being added to C#. All those are super fancy, nice, shiny things that we would like to use, but we don't have an opportunity to do that in an everyday work because obviously it is not, and every project doesn't need all this stuff. So such low-level thing like runtime is a very nice playground for playing with all this stuff, learning how to use it, and also find some bugs even, or maybe playtest just simply all these new features. Also a fun, because it is fun for me to write my own runtime and have it working, because I like that stuff, and maybe some people will also find it interesting and funny. The most controversial part is performance, which is probably bad, obviously, because we don't expect super fast code being executed above 2 runtimes, managed runtimes, but this is the most questionable, and I don't have any benchmarks now, so I will not spend a lot of time describing performance part. So this how you can meet Mobius. The idea has been coined to create something like yikes RVM for the .NET runtime, for the .NET ecosystem. The question is now how to do that. So the design fundamentals look like that. Very simple idea. We have your .NET application that you have compiled in Visual Studio, for example, and you want to execute it. We have Mobius, which is another .NET application running as a .NET application, which is also a .NET runtime. So it is able to execute your .NET app, and it happens it is a .NET app also, so it is running on .NET Core. So we have two levels of .NET runtimes running one on each other, and then we have finally we have this application on .NET application that we would like to run in our Mobius runtime. In the end, we have two layers of JIT code and two layers of runtimes, which seems to be pretty mind-blowing and maybe stupid even, but I will try to show you that it is not so stupid and it may work. So two layers of JIT code, and this slide is kind of most important to understand the whole idea. You have your .NET application that you have compiled and you would like to execute, and this is an input to Mobius, which obviously gets this as an assembly file to be executed. And this Mobius, my runtime, is JITting this application to the native code. This is super important to understand, because this is why this is not so whole stupid idea, because in the end your application is running as a native code that has been JITted by Mobius, and it doesn't care, this application, this JITted code mostly doesn't care whether it has been JITted by Mobius or by .NET Core or maybe by another runtime. It is just native code running your application. So in this sense, it makes sense, because it is just a native code running with the native speed. Obviously, there will be some calls from this JITted code, the code to Mobius, providing some features like, for example, let's allocate me an object or something like that. So yes, there will be some callbacks from the JITted code to the Mobius, and then this code will be managed. And obviously, if it is managed, then it will be JITted by the .NET Core and again run in a native speed, let's say. So the speed of this whole thing depends how often Mobius will do things that requires calling .NET Core. And one of those things is allocations, because this is one of the most typical routine that is inlined into the JITted code. Let me allocate an object for you, or just, in other words, I'm asking the runtime to allocate me an object. So if Mobius will be not allocating a lot of objects, in the end we don't have a lot of calls to the runtime itself, and the code JITted by it will be running with almost native speed. So it really depends how the Mobius will be written, how heavy it will be, and how often it will require to call something more sophisticated. But the most important thing, besides all those discussions, is to remember for you that maybe this seems to be kind of mind-blowing and pretty strange idea, but the whole concept here is about that the Mobius is emitting JITted code, native code, and this native code is running in a native speed. So in the end, that's why it is not twice slower, for example, because we have one runtime and another runtime. It is not, because it is just running, executing in the end the native code. Then we have a decision what to share. So, for example, in case of yikes, RVM approach, some part is shared. We could make Mobius using, for example, the original GC and the original memory management. It could even try to share the type system and other stuff. We could think about such approach, but I was more tempting to create something totally separated, to have this super plain empty page, carte blanche, with a totally new runtime that you need to write from 0 to full runtime, not sharing anything with the .NET Core. And the idea here is to write it in a way that is not using the underlying .NET Core a lot. So Mobius will be mostly here executed, and .NET Core will be called only occasionally. So there was this pretty funny moment in time when I was just doing file new solution to create a new runtime. And then I needed to make a lot of decisions how to structure it. And in the end, for now at least, it seems to be pretty simple. So I have a host, which is a console application, which is for starting the application that I'm providing. Then I have the engine as a core part. And what is most important here is to write it all in a way that will trigger and promote research and experiments. So for example, from the very beginning, I'm trying to write the GC and the JIT as a plugin, as a library, however you call it, to make it replaceable, to make it available for you to write your own customized version. And all this should be plug-enable, in fact, to make all this research possible. And then we have a lot of design decisions, for example, whether Mobius should use async or not, whether it should be interpreted or JIT-based, and so on and so on. We will return to those decisions. Then, obviously, when writing runtime, this is this very long, boring part of and stuff of interpreting metadata and the whole type system, and it is really boring. Like, you need to implement ECMA 335 to understand all the metadata, to understand all the signatures of the methods. It is not super funny, it is not super fancy, but needs to be done, and I'm just doing it. And it is, in the end, one of the blockers for me to open source it. I would like not to open source it before doing this boring part, at least some parts of this boring stuff. But this needs to be done. Then we have the GC, which is obviously my beloved topic. So a lot of design decisions, whether it should be generational or maybe not, whether it should be concurrent or not. A lot of decisions. Currently, I'm not interested in that because it is the second stage. I need a runtime, and then I will just be worried and I will start to think about the GC. The main important thing here is to make the GC as an extension that you can write your own. And pretty important stuff that is in the heart of everything, object memory layout. Like when we have a Mono or when we have a .NET Core, it has its own memory layout that has been designed and decided, and it is nice because they need it. But I would like to write Mobius triggering research, so I need to make it an extendable, plug-enable way that you, as a contributor or as a research, you will be able to introduce your own memory layouts, so you can experiment on that field. And obviously it complicates stuff because object memory layout is super central part of the runtime, so GC and the JIT needs to know it. So I need to glue somehow all the pieces in an extensible way, and this is an important, nice part of the research itself. Regarding async or not, the decision is fast. It is not async because async is for IO bound code for scalability. .NET runtime and my Mobius and any other runtime is not so IO bound. It is mostly CPU bound because it is JITting some code and executing this code. So at least for now, I don't need and I don't feel any need for making it async. So I don't have any async code in Mobius. Flexible object memory layout, as I mentioned, is super interesting research, how to make it as a flexible and customizable way. Some research is being done on this field also in the JVM world. So as we see, there is a lot of field of research, and there is even a truffle special language implementation framework, which is written in Java, that allows you to write your own languages with their own memory layouts. So people are doing that. I'm looking at such projects to be inspired how Mobius can reuse some ideas to do that. But the heart of the runtime is how I'm executing the CIL. I have a set of CIL instructions, and then I need to execute them to make the runtime running my application. And here is the decision whether it should be interpreted or not. Interpreting is super easy concept. So you have an instruction, you from memory, you check what it is, what you should do, and then do it and repeat it. So interpreter is super easy concept. It is just a huge loop over the whole body of a method that come from an assembly file. And then you see, okay, this is opcode, this is opcode LDL log something. So I'm doing something. This is an opcode doing something, so I'm doing this, and so on and so on. This is a huge loop with a huge switch inside, interpreting instruction by instruction. So conceptually it is super easy, and there is nothing more to add, and it is in fact one of the benefits. So it is super easy to implement it because we perfectly know what to do. We have set of instructions like CLI defines around 100, let's say, instructions, opcodes. Then we need to switch all them and make some actions for every of them. So it is super easy to implement. Another, and this is for, let's say, runtime creators, another functional important benefit is that it does not require executable memory region, because it is just an interpretation. So we are taking some memory region and then we look byte by byte and interpret it somehow, triggering some actions. We don't emit any code. We don't need any code to be emitted. And in the end, we don't need any executable memory region that then will be called. This is an important advantage, but obviously there are some disadvantages, like it is slow, and this is the main problem. So it is just a loop, which is very, very bad for branch predictor. It is not CPU friendly, and it makes it running very slowly. There are also no optimizations possible because it is just instruction by instruction, plain interpretation. And another thing for runtime creators, it is not so fancy for learning how you can create your own JIT, because it is no a JIT. There is just an interpreter. So those are the, let's say, advantages and disadvantages. Still, runtimes use interpretation. For example, Mono has pretty well-tested interpreted mode, which is because it needed it for running on iOS, because iOS doesn't allow us to use executable memory region and does not allow us to dynamically create a code. And that's because of that, Xamarin is using Mono on iOS in an interpreted mode. And also the same reason Blazor is using Mono, because currently WebAssembly, which is used by Blazor underneath, does not have JIT, and we don't have this feature of creating and dynamically creating code in browser. So Mono has pretty tested and interpreted mode. .NET Core has an interpreter inside, but it is disabled by default. It was not used in any project. It is there simply because from the historical reasons probably. And .NET Anywhere, that I mentioned previously, written by one guy, is also using sort of interpreter inside, and this is why it was used for a Blazor prototype. As I said, Blazor required to have an interpreter mode. Okay, so interpreting is existing, but it is not super fancy for us. I would like to write a real JIT. Obviously, advantages are that it can be super optimizing. Sky is your limit, and you can optimize it as super sophisticated way as you would like. And obviously it allows you to learn how to write a JIT. So it is, for learning purposes, much better approach. The disadvantage is that it is much harder to implement a JIT because the sky is the limit, and then you need an executable memory region to emit your native code somewhere, which is a disadvantage. But for me, it is super nice to write a realjit, well, however simple it could be, because it allows me to learn and plug in it into the Mobius, so further people will be also able to plug their own. So I needed to write a JIT, not an interpreted mode. But there is something in the middle. When you have a JIT, there is a concept called of the threaded code, and do not mislead that thread here as a thread from multi-threading. Thread here is from as a different meaning of interleaving things. So threaded code is a concept described in Wikipedia, for example, is a programming technique where the code has a form of entirely consists of calls to subroutines. That's why it is called threading, because we are threading interleaving calls to subroutines. And in the end, it is a just-in-time compilation which will emit. We can create such threaded JIT which will just emit subroutine calls for every CAL instruction. That will be simply interpreting stack-based machine that is defined in CLI. So, as an example, if you have ever seen CLI CAL instructions, you will see here what we are doing here. We are pushing some value on the stack, then we are pushing the second value on the stack, and then with the help of the add instruction, we are taking those two values from the stack and putting on the stack the result of addition of those two values. This is how your programs are looking from the CIL perspective. And now if you would like to interpret it, we will be just doing this huge switch over those three instructions. And in case of threaded code, we will emit something looks like that. We will create a code for every of this instruction, and then our code will be just call of subroutines for every of such an instruction. This may seem pretty not optimal, but it is kind of middle ground. Calls are super optimized in the modern CPUs, so this code is obviously will not run in the speed of the full optimizing JIT, but for sure it will be running faster than a regular interpreted code. So we have kind of perfect middle ground. The difficulty is okay. It is good for start. The logic is similar to the interpreter. We are implementing the stack machine defined in CLI directly, so we can omit difficult things like register allocation. But on the other hand, it is a little faster. We have now this huge interpreter loop. And what's also nice, it requires executable memory region. It is kind of real JIT because we are emitting some native code that will be executed. So very nice playground for experiments and tests. Okay, so I described a lot of things, how design decisions looks like, how it can look from the code, simply how it is working. So reading the metadata, as I said, it is pretty boring and there is no rocket science. It is just looking to some data structures. And I'm using here, in case of Windows, a very nice library called PENET, which is a parser for Windows portable executable headers, so DLLs or exe files. And getting into the code that needs to be interpreted and run is pretty simple here. I'm just loading a file of the assembly, which is in this case console app adding DLL. And thanks to this library, I can pretty fast look where is the code of the main method, which is in the end so-called entry point. And then, as you see on the below part of the slide, I get a span which is representing a method body of the main method from this assembly. So only a few lines of the code with a little help of hard coding, which is not necessary to explain here. We have here very fastly span representing CI instructions to be executed. So this is not a hard part. The hard part is how to execute it, obviously. So we need to design the JIT. And here, few things. I need to have a memory region that I will be able to execute. So I'm virtual allocating a memory region with some size, which has this memory protection execute right. So I will be then later on able to execute code that is emitted there. And the very simple thing, I need to implement the JIT with the help of some kind of method, which let's call it JIT emit method, which is taking a method body and it's emitting a native assembler into this region with that I have allocated. Very, very simple stuff, right? And then when I have it JITted, I will need to call this method to have it executed. So the very first thing is how I can call a dynamically created unmanaged code from the managed code, which seems pretty hard. Like I have C# code in Mobius and I have JITted some code to a native memory region, which is representing my code. And now I would like to call it and how I can do it. So for that, we have a calli instruction, one of the CIL instructions, which allows us to call a method indicated by a pointer. Super low level code, super low level instruction is exposed in CLI standard. To get a pointer to it, to get a pointer to a given method, we can use another low-level instruction, which is called ldftn, which allows us to get a pointer to a given method. So, for example, if we would like to write it, we need to refer to CIL instructions, and here we have an example of a method that is being called. I'm putting on this evaluation stack the number 4 as a kind of argument, let's say, example argument. Then I'm loading the pointer to do something method, and then I'm using calli to execute this method. This is all low level because calli instruction and ldftn instructions weren't exposed to C# and still are in fact not exposed to C#. This will change in C#9 that it will be published next month. C#9 is adding function pointers, and this is exactly this. It is just exposing calli and ldftn functions to the C# itself. So we will get a special type of delegate, as you see here, delegate with a pointer that will be able to take an address of a method, and it is a ldftn instruction exposed, and then you will be able to call it, as you see in the use method, which is simply exposing the calli instruction also in the C# itself. So this is all pretty nice that it is being exposed, but for me it is not so, not every scenario is convenient for me because it all requires compile time known delegate. As you see, here we have a delegate that is just saying that I have a managed method that is expecting an integer argument and returns an integer. But when I'm JITting a method, I obviously don't know the signature of the method at the compilation time because it is the code created by the programmer from the external assembly. I'm executing some application. I don't know at the compile time what will be the signature of it. So I need to emit a code in IL that will use calli, and I don't need ldftn function because I know the pointer, I know where I have JITted my code, so I know the address, and I need to create and I need to use this Kali to call this method. And this is the heart, let's say, of this. I'm using dynamic method, which is pretty low level also stuff that allows you to dynamically create a code. And I'm emitting here simply a very simple function that is taking this pointer to this method and emits Kali instruction. So after that, I have a method that will be able to call this JIT code. But here I had coded the delegate. I had coded the signature. As you see, I hard coded it to expect integer argument and a return type as an integer. So I need to create also a delegate in a dynamic manner, because I only during the execution I know the delegate type. So I also needed to create this pretty scary, messy code in C# that is able to create a type delegate with a given parameters and return type. Not super necessary for you to understand it now, but all this creates all the pieces that I can glue to be able to execute dynamically created native code and call it from the C#, which is obviously what I need to do as a main feature of C#, of the Mobius. Obviously, JIT is just-in-time compilation, so I compile everything. It doesn't compile everything in advance. It is just in time, so we are triggering a compilation only when a method is called. So instead of, let's say, JITting everything from the assembly that I'm loading, I need to use kind of lazy JITting to make it a real JIT. So this is obviously working in a lazy way, as I said, and I need some kind of stub that will be an entry point of every method that will be there and wait until this method will be called, and only when this method will be called, it will trigger JITting my method. This is exactly how it is implemented in the real .NET runtime. Just the same concept, some stubs that will trigger JITting, and when I will call this method address, I will call this stub in the end, and this stub will trigger JITting my method and will replace this address with the JITted code, and from now my method address is pointing to the native code that has been JITted. So this is exactly how the real JIT is working, and no super rocket science here. This just needs to be implemented in Mobius. And this is the code, like emit JIT stub is the stub, which is an entry point for every method. As you see here, I'm getting an address of JIT method and emitting this again dynamically, because the signature of this method must signature of this method must be the same as the signature of the method that would be called. So the param times and the return times are all dynamic here. So I also need to dynamically generate this stub, which inside is again calling Kali to call this JIT method. And now we have this JIT method, which is the heart of the Mobius, which is taking a pointer to a method description. And as you see from this pointer, I'm able to get a method body. So I have now a span representing the whole IL body of a method. And the only thing what I need to do now is to emit native code based on this IL body. The only thing, as we can say, it's so simple. And what I'm using here for emitting assembly, there is a perfect iced library, which is a high performance instruction assembler, disassembler. So it is very convenient to emit assembler in this way from C#. So we have some memory region, which I'm here representing as a memory code writer, as you see at the end of the slide. And with the help of those instructions like push, move, sub, I can just write a code that I would like to emit like I was writing just a plain assembler. Here is an example of hard-coded method, obviously. Instead of this hard-coded assembly, I should now implement the whole threaded JIT to emit codes, to emit native code that will be calling routines for everything. But this is the heart of it. Like, we have it, and now we are emitting the native code that then later on will be just called as a native one. The only one thing missing here is that we need to sometimes call the runtime back. So the emitted JITed code, the native one, should sometimes call the Mobius. For example, allocation is one of these examples. So we need a pointer to an allocation method that will be just allocating objects for the application, and we need this somehow to do. So we have a pointer to it and we would like to call it. And how we can do it? Here I must say .NET Runtime, the original one, .NET Core Runtime, and its reverse invoke is doing really nice things, and implementing this is pretty simple. So when you have some method that would like to provide as a callback for a native code, you can use this marshal.get function pointer for delegate method, which is not super maybe well known, but it is really powerful, which allows you to get a pointer that may be used from native code to call the method that has been wrapped with the help of this. So this is exactly what we need. We need to have a callback that will be just wrapping our allocation routine. We are getting a pointer to this with the help of this method. And then from the native code, we can just use the plain old call instruction, and that will call this stub that has been created for the reverse invoke, and it will in the end call our allocate method. This is a pure magic that it is happening in a safe manner. And what's even more funny here, we can get rid of all this with the help of function pointers, which will be even clearer and faster because of, for example, unmanaged callers only attribute that has been added to .NET 5. So again, nice playground for describing low-level stuff, even the newest one, in the context of such a project. This is super, I imagine that this is super hard and mind-blowing probably, but it is really nice to playground, as I said, for learning all this stuff and for experimenting. And obviously now we have the JIT itself to be implemented, so it is a huge amount of work to be done, and this is when is the real problem. The question is when something really working could be created. And obviously the amount of work needed to be written to make full .NET Runtime is infinite, so a single person like me probably won't be able to do anything really production ready in this century, unless a lot of people will help me. And the current status is just to provide some kind of vertical proof of concept that we can do it with not supporting many stuff, with a very simple GC, with maybe not supporting generics. A lot of things we can cut off to make vertical proof of concept. And the goal is to open source it, obviously, because I hope that people will be interested. I hope people will be invited to experiments to learn how you can how the runtime is working, because there is no better way of learning how the runtime is working than writing your own or helping to write your own. And if you have dreamed of contributing to .NET Runtime and you are scary of that for obvious reasons, Mobius should be motivating to do that. And that's because of that, I really would like to make it open sourced as fast as possible. The only thing is I don't want to make it too fast open sourced, because people will be probably discouraged by the number of missing features. So I need to find some perfect spot to make it available as fast as possible, but not too early. So there is this blog post here that is summarizing the thing that I mentioned, and I have 8 seconds left. So this link is currently private, the repository on GitHub, but I hope it will be soon open source. And that's all. Thank you.